A Danielle cell is a copper zinc, kind of a standard, kind of classic one. Remember that where we have the zinc undergoing oxidation, that's the anode. Anode is oxidation. Copper being reduced, that's the cathode. And then just all of these, like applying all of these concepts. What is being reduced would be the copper ions. What is losing electrons would be the zinc. And again, these answers were on that one I went over, but the anode oxidation, the anode is the zinc cell, basically the zinc cell, and the cathode is the copper. And the direction of flow is always anode to cathode. And I'm talking about the flow of electrons. So we had the electrons going from the zinc to the copper. We are actually going to skip the electrolytic cell. It's sometimes done as a demo, but we're going to skip it. We're learning our first electrochemistry in lab, so let's go to our half cell potentials and what we're going to be doing. We're going to be measuring, so we're labeling some of these terms. E cell is, E stands for electromotive force, and that just means tendency to move electrons. And so it's because of the move electrons that it's called electromotive force. It is measured, and again, we call that potential. That's what I've heard most often. And electromotive force, it's measured in volts. It's the unit, and we can think of it as electrical pressure. On our setup here, what we're going to do is we're going to use zinc as one of our half cell reactions, and then I have X here because we're going to switch this out. We're going to put different metals here with their solution and read the voltmeter on each one. So zinc, in most of them, zinc will be the anode. And so I should tell you that it's switched in one reaction. Because it depends on what the metal is. It depends on which metal is more likely to give away the electrons and which one is more likely to accept the electrons. And so this voltage is what we're going to read. And that will tell us the potential of the whole cell. And we know that zinc, as an anode, its potential is positive 0.76. And so when we read the voltage of the whole thing overall, we will be able to determine the voltage of this half cell, whatever metal is going on. We have happening here. Let's see. So this is the cathode, and we're going to figure out its reduction. And this one that we read up here is like the total of the two. So it'll just be a subtraction problem. So here's what I was just saying, that this will read on the voltmeter. This you can look up on a table. This is for the oxidation potential for zinc. And then this one is what you're going to be determining. This is going to be the potential. And most of the time it'll be a reduction potential, except for the one that it's switched, for the other metal. As I said before, when I was saying it being switched, what I'm talking about is that in one, zinc is the cathode. And so the electrons will go the other way. Most of them, they will be going this way. But if the other metal is the anode, then they always go away from the anode. So how we handle that, so this is for zinc, and we know its oxidation potential. Guess what its reduction potential is? Well, it's the opposite, so it'll be the opposite sign. And so that's always true, that these are always the same number, opposite sign. Okay, some basic stuff here. Metals tend to gain or lose electrons. In general, they give up electrons. When we say a metal is more active, so active, they tend to be easily oxidized, because oxidized is what metals do. They give up electrons. So oxidized means giving away electrons. And we already said this. These two potentials are the same number but opposite signs. So a more active metal has a high positive oxidation potential and a negative, we would say small, but really small is negative. That makes sense. Reduction potential. Okay, and we've kind of already said this, but let's just write this down and make sure we got this. This is how you're going to do your calculation. Okay, this is from the voltmeter. This is given. And this is what you're going to determine. For whichever metal you're dealing with. So if this number, maybe it's, so you get a number over here, you read off, let's just say you read 0.95 volts on your voltmeter, and then you know this is 0.76. So then in this case you would say it's 0.19, just subtracting. Okay, this is what how the tables look. The tables where you could look up potentials for each metal and its half-cell reactions. And there are different types of activity series. Sometimes you get an oxidation potentials, a series of oxidation potentials, and sometimes you have a series of reduction potentials. And you can always tell what you have if you look at the reactions. They always have the reactions over here. These are oxidation reactions. And so I know which one this is, because remember that this is, I could write it like this, oxidation potential. If I wanted the reduction potential for this reaction, it would be the opposite reaction. It would be A plus an electron goes to A. If I flip that reaction, the reduction potential is just the same number, opposite sign. So that's why you only need a table for one of them, because if you need the opposite reaction, you just flip the sign. Okay, and remember that on an activity series, positive is spontaneous. In other words, I would say positive is good. If you have a really positive number, that means you have a good anode or cathode. So let's just look at that. So since this number is the biggest one, whatever this A is, it's really good at being oxidized. It's biggest positive number. So that means it's the best anode. The oxidation reaction is very favorable. Could do the same thing for this one. It's not a very good anode, so it's the poorest of these, anode. But if I think of the opposite reaction over here, the opposite reaction, reduction is favorable. So this is it's the best cathode. So let's answer these questions. Which metal is most active? Remember, when we talk about the metals being active, what metals tend to do in general is be oxidized. They're the ones that are oxidized. So we want to have the one with the high oxidation potential, and that would be A, which has the greatest reduction potential, and we already figured that out. It is C. So there's opposites there. Okay, we're also going to look at the effect of concentration. And this has to do with Le Chatelier's principle. You can probably guess pretty intuitively that those solutions are pretty important, and the more concentrated they are, the higher your voltage is going to be. But we can explain that in terms of Le Chatelier's principle. You can think of the voltage, the potential of the cell, as being a product. And if it's a product, then you can just apply Le Chatelier's principle. If I lower the concentration of this ion, so this is one of the ions that is in one of the half cells, that would cause the reaction to shift to the left to replace it. And that would cause the cell potential to decrease. And the opposite would be true. If you increase the concentration of the ion, whichever ion it is, the cell potential would increase.